So I change the agenda a little bit. I'll write that down so that you know what to expect. So I'm going to first do the topic that was going to come later. I realized actually reasonably elementary, but new. I mean, it's something that many of you wouldn't have seen, so I'm going to do that first. Then SVD. Then the SVD for very large matrices. We'll define what massive matrices are. It's like big data, but we'll define that. So I'm going to talk about one particular sampling procedure, and I'll tell you what it is, but it turns out to be useful fairly widely, right, for matrix problems. So this deals with quote-unquote big data, right? It's a tacky term that's bandied around a lot. But here's our technical definition of big data. It's just something that doesn't fit into RAM. So usually you think of algorithms like SVD and so on traditionally, if you will. Most of the time you think of the matrix being in RAM. And then if I want to access one particular entry, I get it in unit time, any entry, right? That's how you reckon the cost. But that doesn't work for big data. So the data is outside, and we have to worry about what fits into RAM and so on. We won't get our hands too dirty. We won't worry about exact transactions, input, output. You'll see we'll find a clean way of doing it, right? So an obvious thing when you encounter a very large problem is sample. So let's say I have a very big matrix, too big to fit in RAM, and apply my algorithms. I like to sample some rows and columns and do whatever computation I'm going to do. It could be singular values, which I haven't defined. I'll define when we come to it. It could be singular values, or it could be, today we'll see something as simple as matrix multiplication is interesting. So we would like to deal only with the sampled rows after that and get an answer. Of course, this is not always going to work, right? Indeed, one thing that certainly won't work is uniform random sampling. So if I pick rows all with equal probability, there's no chance that I would get a result, an error bound, which works for all matrices. In a minute, I'll say that. We want things that work for every matrix possible. And the reason is simple, right? So it may be that in a matrix, a small fraction of the rows are very heavy and the rest are 0 or close to 0. We have to be able to handle such matrices. Again, I have to tell you in what way we want to handle them, what the error bounds are. But intuitively, uniform sampling won't do. We have to pay attention to how big or small the entries are. So we'll see. I said this lecture 2 problems. I may not get to both in this lecture, so it may involve part of the next lecture too. So one is a very simple thing. On the other hand, it'll be quite useful for the next thing, which is not so simple, matrix multiplication. So I have 2 matrices and I want to multiply them. That's all I want to do, right? I want to do it very fast with sampling. We'll see a way of doing that. Again, I want to get an approximate answer where the error is bounded for any pair of matrices you give me, right? Not random. But the next thing is something that perhaps you wouldn't have seen generally. So it's going to use matrix multiplication result in a funny way, in not the way one might be thinking of, but we'll see. But we want a compressed representation of a matrix. And I should have said that there, but the compressed representation of a matrix is the following. What we will prove is that any matrix can be approximated given a small sample of rows and a small sample of columns. So I want to get an approximation to every entry of the matrix, and the claim is this is non-trivial. We'll prove that perhaps only by the next lecture. But the claim is that whatever matrix you give me, if you give me a sample of rows and a sample of columns, that suffices to approximate the matrix. But The magic bullet is the probability distribution with which you pick the rows and columns. Probability for sampling. Okay. And as the title of the lectures indicate, probabilities are going to be proportional to the squared length of the rows and columns. We are going to deal only with real matrices, no complex entries. So I square the entries and sum them up. The probabilities will be proportional to that. This theorem will not be valid. It's not known to be valid if I cube the entries or take the absolute value or any of those things. It's got to be square. And then we'll prove that for every matrix, you get an approximation to the whole matrix doing this. Okay. We'll come back to that. I first want to do mostly multiplication. Both will sample rows with probability proportional to length squared as well as columns. Just the length squared as a vector, sum of squares of the entries. Okay. That is the magic bullet. We'll see why length squared is the right thing to do, but it turns out it does a lot of things. We'll also use length squared later for SVD. Length squared sampling has been used for a whole number of things. We'll perhaps see some, but not many, too many. For instance, there's a way to deal with tensors using that. We'll see perhaps later. Now, throughout this talk, so there are two sources of randomness in algorithms. One, you can think of them as either the algorithm tossing coins or the data tossing coins. So what do I mean by that? The algorithm tossing coins just means there's a random number generator available to you. Okay? So you can generate random bits and base your decisions on that. These are often called randomized algorithms. The data tossing coins means average case analysis. That is, I'm not able to prove for every input something happens. I'm only able to prove for the average input. I take the expected time over all inputs. We do not want the data to be allowed to toss coins here. We want to be able to do something that's good for every matrix. So data does not toss coins for these two things I'll do, right? But the algorithm does. So algorithm is randomized. Okay. You could have both. You could have only the data tossing coins. You could have only the algorithm as here, or you could have both. All of that is possible. Okay. So matrix multiplication, so it's just multiplying two matrices, right? So we have m by n and n by q matrix A and B. I want to find AB. If you want to do it exactly, you can do it in m and q time, of course. And you've all seen a lot of divide and conquer algorithms which have numerical problems, but they improve the complexity. So I would like to do matrix multiplication approximately, in a sense we'll define in the error, in linear time. Linear means m times n plus n times q. Okay. Now, later I'll talk about sparse matrices where many entries are 0. You can do it in linear time for those as well. So we will do that. And one reason you might want to do it, approximately instead of exactly, is A and B cannot be stored in RAM. They are big data, so we want to sample and do this. This will be based on sampling. Okay. Can we just take a sample of A and B, multiply to get an approximate product? That's what we'd like to do. Well, we can't sample entries of A and B because you don't know what to multiply then. You don't have compatible dimensions. Sample some rows and columns of A, B. Which rows and which columns is the question, right? Do I sample some rows or columns of A and disjoint from that? Do I pick some rows and columns of B? And you'll see, well, you'll have to think about it. Suppose I pick arbitrarily some rows, let's say, or columns of A, but I don't pay attention to which ones I picked, and I go to B and sample. You should be able to convince yourself not much can happen. You cannot do that. You cannot do this. So that's also not going to work. But observe the following. The product AB is just a sum of outer products, the first column of A times the first row of B. So the column of A, first column of A is a column vector, first row of this. So let me write this as A1 dot, I guess, sorry, excuse me, I think I used this notation, A1, what is it? So I think, something like this. It's for the first column of A, and the first row of B is this, right? So if I multiply them, I get a full vector, right? So this is m by 1, this is 1 by n. I get a full vector m by n matrix. So that's a rank 1 matrix. Okay. I don't know whether you all seen this identity. It's very simple, but it's worth checking the first time that that is correct. Okay. So the matrix product is exactly just a sum of these n is the middle dimension, right? N outer products, right? And rank 1 things. You should check that at home. It's just by multiplying matrices. There's no magic to that. So the right-hand side is the sum of n quantities. It happens to be the case that each matrix, each quantity is not a real number, it's a matrix, it's a full matrix, right? But nevertheless, the sum of n things. Okay. Now, the first thing you would think of to evaluate a sum, at least if they were reals, I would pick a sample of r of these n quantities. And if the sampling probabilities are correct, that is, if the variance is not very bad, then you hope that their sum, you have to scale it by n times r to make it unbiased, right? You picked r out of n, you have to make it unbiased by doing that. You would hope that that's a good estimate. That depends on the variance, right? It's not going to be a good estimate for all probability choices. In fact, it won't be a good estimate for the uniform choice. That's not difficult to see. So if I pick columns uniformly at random, that won't be a good choice. But this tells you something very crucial. So I'm going to sample some of the columns of A. I must pick the same rows of B, right? This is the sum. So first column times first row. Okay, so I cannot pick disjoint sets of columns or rows of B, right? Whatever columns of A I pick, I must pick the same rows of B if I'm going to plead to this, this identity to argue that things are good, which is what we'll do. Okay, try uniformly at random. So UAR refers to uniformly at random. If I pick uniformly at random a subset of columns of A and same rows of B, okay, does this work for every A and B? Okay, so let's think about that for a minute. Can you give me examples where it doesn't work for some A and B? What's an example where if I picked uniformly at random some sample of R columns of A, same rows of B, right? I have to do that. I would get nothing. I'd get garbage maybe. The other possibility is A has only one non-zero column and B has the corresponding non-zero row, rest are zeros, and you'll never pick that, right? So if A looks like a non-zero here and all zeros there, and B looks like non-zero here, all zeros here, this is A, this is B, then AB is not zero, is not the zero matrix, right? Because you get that out, this outer product tells you something. But if R is not n, R is not as high as n, you would almost never see this column, right? The probability is only one n, and unless you pick n samples, you won't see that column. Uniformly at random, you're sunk. Okay. Now, there is a simple fix for this example. So this A and B, non-zero, zero, non-zero, zero. And here, if I pick a column of A with probability proportional, this is proportional to its length or length squared or any of those things, then you have a chance. There is a chance. So if I did that, I would pick the first column of A, right? That's the only one that is non-zero, so the probability is 1 of picking this and 0 of picking everybody else, and I'll get some result. You hope it's right. Now, this does not say you have to do length squared. We'll see why later, but something depending on the length, right? So you have to do importance sampling. Importance sampling just means that the probabilities are not uniform. Yeah? Yeah, so I have not put up the error metric yet, I'm sorry. I will put it up, but for that I have to define a norm and so on. What I want, okay, I should tell you. So I want the norm of AB minus my approximation. And the norm I want is just the sum of squares of all the entries. Square. So I want the mean squared error, if you will. So Frobenius norm. Yeah. I want the mean squared error to be small. Okay. Now, small, so this is a square here. Small in what sense? In this sense. I'm jumping ahead a little bit. This is the mean squared. This is the square of sum of squares of all the entries of A. This is of B. I want my error to be less than or equal to that times some epsilon. Okay. Again, I will state this more carefully. This will not be true for this matrix if you do uniform sampling, right? You'll get 0 and it should be non-zero. Okay. So this does not work. Matrix multiplication continued. So we write the sum. I'm going to just write it in this sort of MATLAB-ish notation, right? So column I of A, column row I of B. Uniform summing does not work. I'm just repeating that. General non-uniform sampling, I'm going to pick column I of A and also the same row B with probability Pi. So P1 through Pn, or some non-negative real summing to 1. P1 is the probability of picking column 1, P2 is the probability of picking column 2, and so on. I don't know them yet. I'm trying to find them. Okay. So the experiment I'm going to do is pick a J, one of the columns. Probability of picking J is Pj. Okay, it's one trial I'm going to do. And I'm going to define a random variable x. It's a matrix valued random variable, right? It takes on matrix values, not real values. And the random variable is going to be the picked column of A times the same row of B. So it's one outer product, right? I'm picking one column, and I'm going to estimate the entire sum by just one, which is not going to give you very good error, but we will take an average of many things later, and then it will give you a better error. So x is a matrix value random variable. And really, ultimately, we'll want to take IID samples or IID samples of J and take the average. Otherwise, the variance will be too high, right? But let's deal with one and find the variance, and we can compute the variance for average of many things simply. Okay, so let's compute the mean and variance of x. And again, once I know that, I know the mean and variance of the average of our trials, right? So what's the mean of x? So it's a matrix value random variable, so the expected value should be taken entry-wise, or the other way of saying the expected value is also a matrix, right? So let's see what the expected value is. These are simple things, so I'll go over perhaps a little faster. So the expected value is just with probability Pj, I'm picking J, and I get this, right? But this is not unbiased. So the expectation, I like the expectation to be A times B. I'd like this expectation to be the matrix A times matrix B, right? It's a matrix. And I want that. That's what unbiased means, right? So any idea of how I can make it unbiased? But first, maybe a hint. Step back. Suppose I want to estimate the sum of n real numbers, just real numbers now, not matrices for the moment. I want to pick 1j with probability. These are the probabilities with which I pick them. How do we scale the aj so that it's an unbiased estimator of the sum? I want to define a random variable like x, right? I pick a j. X is my aj that I picked, but I want it to be unbiased. I want the expectation to be the sum. So how will I do that? Some little thought about statistics. So I have to scale it, right? So it's, I think I put it down. Yeah, so it's just aj over pj. So I pick a j, right, and then that's aj over pj has the correct expectation. It's unbiased. Okay, so we do that. So that's, okay. So I'm going to write 1 over pj. It better have pj positive, right? Some pj's might be 0, in which case you'll never pick them. So this is all right to write still. Okay. What about the error? So now the variance, right? We have to worry about the variance. That's our main problem. Try writing down the variance of one entry, ij. So instead of variance, try the second moment. The second moment is, so there are L choices. With probability PL, I pick the Lth column of A and the same row of B. So with probability PL, I pick the Lth column of A. And the same row of B. So the ijth entry of the product is A, I, L, B, L, J. Right? So my random variable, X, the ijth entry, I should have written this down perhaps, is this over PL. And so the expected value of Xij squared is sum over L. So this is with probability PL. So one trial, I'm picking one of those. The probabilities are PL. So I'm just writing the second moment down. So I get PL is the probability of picking it, and that's written down there. PL squared, and I get AIJ, AIL squared, BLJ squared. Okay. Now the variance is slightly smaller than that, right? The variance of Xij, so you all know this, right? This second moment minus the expected value squared. But the expected value does not depend on P, the PL, right? So this is unbiased, so it's always the same, so I might as well. So what I'm trying to do is figure out PLs that are good, that minimize the variance. So how do you bound it? Okay, sorry. So there is that question. Okay. I want to say that I can disregard this term and only look at this term, because this is constant. My variables are the PLs, and I'm trying to minimize the variance by choosing the best possible PLs, and it doesn't matter. This doesn't matter. This doesn't depend on the PLs. It's unbiased. So only the second moment matters. So the difficulty is we have one variance for every entry of X. Which one do we minimize? Well, I'm going to take the sum. It's a simple idea, but it simplifies matters a lot, you'll see. Without that idea, life would be complicated because each variance is different. But I take the sum of the variances of X. So let's denote for a matrix valued random variable X, let's denote variance of X to mean the sum of the variances of all the entries. Each entry is a random variable, sum of the variances of all the entries. Okay, and we calculate that. So we get, so it's the sum over I and j of the variance of the entry, sum over I and j of that, sum over I and j of that. This is what we wrote down in the last slide. And simply, this simplifies a lot just because you can switch the sums. Okay. So sum over L, that 1 over PL has come out. Sum over I and j, you get these two, right? Okay. Sum over j of Bij squared is just a column, is just a row sum, right? L is the same. Sum over all j, that's the length squared of the row, because sum of squares entries. And this is the length squared of the column away, right? No, nothing, very difficult here. I mean, just. So now I ask, what's the best choice of PL? So I want to minimize this. PLs are at my control, right? I can choose any PL I want, let's say for the moment. What choice of PL would minimize this? It's the one that minimizes the variance of X. I want to minimize that. Suffices to, okay, I'm sorry. This is something I said here. So instead of minimizing the variance, we can minimize the second moment. Since the expected value, this term is fixed. Okay. Again, I'm summing over all ij. So sum over all ij here too, right? But the unbiased means every entry has the expectation which is fixed. It's independent of P. Okay, so I want to choose the P's to minimize that. So again, I rewrote that. Choose the pk. I guess I didn't rewrite it. I changed the L to k. So I want 1 over pk times that to be minimized summed over all k. P has to be a probability vector, right? So I have to sum to 1. And calculus, which you should do at home. So if you have a1 through an, which are positive real numbers, I want p1 through pn, so that aj over al over pl sum is minimized, subject to non-negativity and summing to 1. And calculus, you have to do this. Maybe we can just do that. So the point is that I'm differentiating with respect to PL and right, so you get a PL squared in the denominator. And so you have to work this out, but that just will tell you that the PL are proportional to square root of AL. Okay? Just because you get the square here, that's all that's happening. You get square root, check, okay? So the best choice of PK are proportional to the square root of that. That's the product of the lengths. Okay? So you can take PK to be product of these two lengths divided by the sum of all the products. So this is, the PK have to sum to 1, so I have to normalize that. That's what I've done there, right? Now, in the important special case that B equals A transpose, believe it or not, it's a fairly important problem to multiply A with A transpose. Now, I'm not actually going to go into details of this, but let me back off one step and say why this is important. Actually, this whole sampling issue came from a more general problem of estimating the variance-covariance matrix of a probability density. So suppose you have a probability density in D space, so some samples, and I want to figure out the variance-covariance matrix of that. Unfortunately, that's denoted sigma, matrix sigma I. So this is a random x. X is a point, right? Sigma ij is the expectation of xi xj, provided after centering. So the expectation of x is 0. So 0 is the expectation of the vector. That means every component is 0. Then I take ijth entry of a matrix to be this. This is called the variance-covariance matrix. So a question that actually originally led to all of this work in a way that probably I won't describe is the following question. How many IID samples? So this is an aside, so if you don't know some of these terms, don't worry. It won't be necessary for later. How many IID samples from A? I'm going to leave a blank here, probability distribution in RD do we need to approximate sigma to relative error epsilon? What that means is I must get a sigma approx that has the property that the quadratic form is within 1 plus or minus epsilon of the correct answer. For every V. Okay. So the question is, how many samples do we need? Because this is a very important quantity estimate quite often. How many samples do you need? But the error definition is very important. Without exception, for every V, you must have that the quadratic form is within 1 plus or minus epsilon. So this question arises naturally in, for instance, in regression, but it also arises in a lot of contexts. Now, so it's not for a general distribution. So usually we worry about what are called log concave distributions, and Gaussians are among them. Okay. And the answer we know now is order d log d. We didn't know that till perhaps 10 years ago, but now we know that for every log concave density, it suffices to pick, divided by epsilon squared. It suffices to pick this many samples. And then the theorem is that the sample variance covariance matrix has this property. Okay, is a decent approximation to the variance covariance matrix of the entire density, right? So I won't prove that. And again, I'm only stating this as an aside, although this was the original motivation. But if some of these terms are not familiar, don't worry about it, and it won't be needed in the sequel. Yeah, sorry. Yeah. So we do need the multiplicative guarantee. So the least eigenvalue has to be captured right. Yeah, that's why you need this, yeah. In fact, for linear regression, you need the least one. So, yeah, that's why this definition. So this originally arose, so this arose in the context of computing volumes of convex sets. And Lowas and I formulated this thing, and then we proved some bound and went through a bunch of iterations before we got here. These results are due to Rudelson, who's a function analyst. The proof was very complicated, but now we know actually much simpler proofs of this. Okay, aside over, let's go back there, right? So in this important special case, we get pk equals the length of the column A squared divided by Frobenius norm. This is the norm of the matrix, which is the sum of squares of all the entries. That's the right scaling factor, right? Because the numerator is this. You have to normalize to 1, so I have to divide by the sum of all the columns. So that's that. Okay? So hence the name length squared sampling. Okay? So it came up naturally here in this context, right? It's what calculus told you was the minimizing probabilities, length squared sampling, right? So that's why you don't use length or length cubed or any of those things. Length squared is exactly the thing that minimizes that. So that's because of this business, right? So so this is called length squared sampling, and that was the title of this talk. And so, for instance, if I use any of these, okay, let's go over this in detail. So I'm going to use, I'm using these probabilities, right? PKs. I'm going to plug them in. The variance becomes, I'm going to plug them into that. That's all I'm doing, right? So that's that guy. PK is this thing divided by the sum, so that comes up here. So altogether you get, this thing cancels, and you get sum over L, length of the column, length of the row. After I sum, I square them, and that is less than or equal to that. So now why is that? What inequality am I using to get that? So what am I doing? So let's, instead of writing all those complicated things, let's write sum over L, AL times BL squared. AL is the first one, BL is the second one squared. I'm saying is less than or equal to sum over AL squared, sum over BL squared. And now we know the name for it, right? So this is Cauchy-Schwarz, right? Or another way of thinking about it is the dot product of two vectors, vector A and vector B, and it's just saying the dot product is at most, dot product squared is at most the sum of squares, product of the squares of the lengths, right? You get the same bound if you used just AK squared. So maybe that's worth doing. So let's just do that on the board. If pk equals a k squared divided by af squared, then I plug it into the top there, and I get the same answer as I was getting there, right? So 1 over pk, a k squared b k, right? Squared. So this AK squared just cancels out, is also, in fact, in this case, is exactly equal to AF squared, BF squared. So these probabilities are the best. This is not necessarily always as good, but the final lower upper bound is the same. Okay, so these probabilities are the best, right? So if the length of the kth column of A sometimes is very high, and at the same time the length of the kth row of B is low, then this is a better thing. But that's the best possible. So length squared is optimal for AA transpose, which is our basic problem. Okay, so that's just, I think that just said that. It turns out approximate length squared is also fine. It gets you a good result, good enough result. If I knew only within a constant factor, I need to know that the probability of sampling is at least a certain amount. At most is not enough. I need to know at least for every k, for some constant, then you get as good a variance. Now this is useful because there are matrices for which you don't want to take the time to estimate each column's length. And then if you know an estimate which has this property, that's good enough. Okay, so so that's what it says here, right? It may be possible to find such pk more easily than finding all lengths. Okay, in that case you can use that. Then you get that. So the unbiased estimator still divides by pk, of course, the probabilities, right? Whatever it is, it divides by that. Okay. And then you get the variance, you get an extra c there. That's just very simple. pk has an extra c compared to what we had. I don't know why I wrote 1 over c squared. Excuse me, it's 1 over c. Okay. So reducing variance is a standard. Let's run over this. So this x had variance less than or equal to that. That's not good enough. Why? Because the Frobenius norm of A times B is at most a product of Frobenius norms. You have to prove this, right? But it's not very difficult. It's just a lot of algebra, perhaps, but it's a norm. It's submultiplicative. It's not difficult to prove. You can do this by writing down entries, which is laborious. But you know, whatever. There are lots of ways of proving this. I won't do it. You can check that. Equality could hold. So even in the best case, if these are equal, that's the best possible, that's the highest possible ABF. Even then, you get the error, which is, you know, if variance is only that much, it's not so good. Variance, in general, this guy is greater than the Frobenius norm of what you're trying to find. It's not a good idea to have error greater than what you're trying to find. Pardon me, I should have had a square here. So this is variance of x. X is AB, two things. Variance is a square, so square, square. Okay, so that's not very good. What do? What's the general method of reducing variance? We take SIID copies, variance cut down by a factor of S. So with that, I'm going to state this as a theorem. It'll be nice if you can remember this. This is a theorem we'll use for doing lots of other things like compressing a matrix. So you have an m by n by q matrix, and we say that we want this. We get it approximately if C is the following. You pick J1 through Js, S samples, IID trials with probabilities Pj which satisfy this property, basically length squared, right? Pj is proportional to the squared length of the column J. Approximately, you're off by a factor C, a little c, and then you form those columns, you pull out those columns, you have to scale them. This is making it unbiased, right? That's your matrix C. Okay. B curl, B tilde is the matrix of corresponding rows of B. What did I do here? I picked one sample and I said take an outer product. This is sample 1, J1. And then I wanted to take J2, take the outer product, and so on. Instead, I just said, put these columns into one matrix. That's the same as saying J1, Js, that matrix times other matrix, right? Because matrix product expands into this. That's all I've done, right? So I was taking the average of S of these sampled X's, and that I'm just writing it as a matrix, that's all. Okay. Then the expected value, so what we have already proved is that the expectation of this is less than or equal to that. This was the variance, right? So its expectation was square. But so AB's mean was CB tilde. We've proved that. It's unbiased. So the expected value of this is that. So I'm taking the matrix, the random variable. I'm sorry, I'm taking the random variable, subtracting its expectation, and taking the square, and that's a variance, right? The variance is this much. We proved that. We proved the bound of the variance of the matrix, and that's that. And then, so if you want just the expected value of the Frobenius norm, that's at most that. So everybody, you know, how does this imply that? Everybody knows that, right? Oh. Same should hold. Same absolutely holds for picking rows of B, correct, and the corresponding columns of A. I could have done that. So that's actually a good point, because sometimes it may be easier. Yeah. Yeah, so it may be, that's the thing, it may happen, like what you're saying, right? It may happen that B is something I know better. I know for some reason distribution of the length squares of the rows of B, or if they're physical matrices, you would potentially have an idea what the length squares might be. And then you would do B instead of A. Either is fine.
I was just wondering, in terms of what bound is saying about, this is a general bound. This is true for any distribution of the energies of columns of A or columns.
Absolutely. Any A and any B, this is true. Yeah, so that's another point worth making again, that it's true for every possible A and B. And in these contexts, it's not interesting to prove results that hold for most A and B, because those are very simple. But, yeah. The best, the optimal ones are A times B, right? That's what you're saying, right? So the optimal choice was length of A times length of B, instead of just one of them. I mean, this is the optimal choice. So if the lengths of all the rows of B have the same length, this can be cancelled, and you get not length squared sampling, but length sampling, right? So length squared comes from AA transpose. Length squared comes from AA transpose, right? In AA transpose, it's length squared. And that was the central problem. Variance covariance matrix was the central problem you wanted to solve. So it's best and easiest to remember matrix multiplication theorem by these words. We'll use them 2 or 3 times, but so it's nice to remember these words, right? So all it's saying is that the Frobenius norm error, which is the second thing, let's say, if you will, goes down as 1 over root S, where S is the number of sample columns you pick for length squared sampling. Okay. So, I mean, clearly the error will go to 0 as you go to S goes to infinity. It's saying it goes to 0 as 1 over root S. Okay, if you look at Frobenius norm. If you look at Frobenius norm squared, it goes down as 1 over S. Okay, and for this case, it's the best you can do. You can't beat this 1 over S. So in general, all sort of simple improvements of this are ruled out. Let's just go over that. Let's see whether, I don't know whether the one that you're suggesting. So what you would like is, what you're saying is, I would like the expected value of AB minus its estimate. So you would like this to be epsilon times the Frobenius norm of AB, right? And length squared will not get you that, but so okay. So if you're interested in the subject, I can give you references. Since this is early work, this is 20 years back, let's say. So there have been a lot of attempts at getting relative error, and there are some possibilities, but much more complicated probability distributions are involved. You have to sample columns according to what's called leverage scores, so it makes life more complicated. So I won't do it here, but I can give you references. So something like that is possible. I'm not quite sure in this problem, but it's possible. So this can be much smaller than the Frobenius norm of A times the Frobenius norm of B, right? This may be much, much bigger than this thing. So that's our problem. We're getting a very large error somehow. So let me state it for 3 tensors. So suppose Aijk, ijk going from 1 to n is a collection of numbers, and I want to maximize over all unit vectors x sum of ijk, aijk, xi, xj, xk. If I had just two indices and A is symmetric, this is an eigenvalue problem. This is the maximum eigenvalue. For three indices, these problems are NP hard. We don't know how to solve them exactly, but the result, the theorem is, can find this 2 plus or minus, well, it's really only minus, epsilon times the Frobenius norm of A, which is this quantity. Using length squared sampling is fairly complex. Again, it's just stated, right? I mean, I won't be able to prove that, but that's true. Again, for every tensor, any aijk. I can give references to all of these if you are more interested. In polynomial time and so on, but exponential and epsilon, 1 over epsilon. So epsilon is an important parameter. You can't drive this error down to too small. That's difficult. Okay, so big data. We are going to implement this algorithm with big data where the data doesn't fit into RAM. How do we do that? Big data means it cannot be held in RAM. That's again our definition. We do one pass through A and B and compute all the probabilities pk. So remember, pk could have been either only dependent on the length of columns of A, or it could be columns of A times columns of B. We had several candidate choices for pk. We can find the probabilities in one pass by just keeping running sums, right? So we do that by running sums of columns. Then we store in RAM each of the pk's. Everybody with me on this, how we do this? I mean, we got to compute the length squared of each row of A, sorry, each column of A, okay, or each row of B, or the product of the column and length. You have to compute that for each one, then we have to normalize. At the end of the day, we find the sum and divide it, so normalize by 1. Okay. So we can do this with just order n space, not n squared. The RAM still uses n space instead of n squared. With pk on, once you have the probabilities, we can toss coins offline to figure out which set of columns, which set of S columns of A and the corresponding rows of A we are going to sample. Okay. We do this, and then we make a second pass. So I'm thinking of now A and B as too big to fit into RAM, so they're in external memory, and the only way you can access them is by making an entire pass through the whole thing, right? I cannot get one entry. I can't randomly access one entry, so I have to make a pass through the whole thing, right? So you can make a second pass through A and B and pull out the sample. Okay? So in two passes, and then multiply the sampled matrices in RAM because they fit into RAM. Okay? And for error, okay. So if I want error less than epsilon times this, S has to exceed C over epsilon squared. Okay. Now, what I told you here seems to be a way of picking one sample column or one sample column of A and row of B. How do I do S of them? Only two passes. I'm not allowed S passes. So you know all the probabilities, so you toss coins S times instead of one time. And the S coin tosses tell you which S columns I must pick. And then on the second pass, you pick them all out. Okay. So that's something simple. Then in two passes, you can do this algorithm. With, well, okay. So yes, with replacement. But it's highly, okay. So some of the JTs might be equal, right? That's what you mean. But, you know, with high probability, that won't happen because, but yes, but with replacement. This whole thing is. Actually, there is a, okay, so this, I mean, there's an old result of Hefting that says that without replacement is always better. Sorry, with, I forget, the variance is bounded 1 by the other. So, because it's a convex function. But yeah, so, but I think, well, what I'm talking about is with replacement in any case, for simplicity. Okay, now, just a list of problems that now we know how to solve. I won't go over any of them except the one I've told you. Sketch is compressed representation of matrix, which I will go over. That's our next topic. PCA, principal component analysis, SVD, it's coming. You can actually compute the SVD by sampling. That is, we'll be able to sample, again, length squared. We'll be able to sample by length squared probabilities, the rows of a matrix, and do SVD on just the rows we sampled. And we can prove that that has an error bound compared to what you would get by doing the SVD of the whole thing. I'll do this after I introduce SVD, vanilla SVD, and plain SVD, and then talk about it for a couple of lectures, right? That's our next topic. After that, we'll see how to do this. Okay. Tensor optimization, you asked. I won't do it, but again, well, I stated the result at least. Okay. Graph falsification, again, I can give you references, but I won't do that. Okay, now sketch of a large matrix. So that's our next topic. I may or may not quite finish all of this today, but we'll go into this and then come back if we run out of time. So what do I want to do? I have a large matrix. We'll show our theorem is A can be approximated given just a random sample of rows of A and a random sample of columns of A, provided sampling is length squared. It's not known for any other probabilities, right? The errors are too much. So for length squared, we'll be able to prove that. So let's say first intuitively, let's ask ourselves, can we approximately sketch a matrix by a sample of just rows? The answer is obviously no, because the sample tells us nothing about the rows that we didn't pick. They could be anything, right? But suppose the rank of A is K, which is very small compared to M and N for the moment. So we want to do it for high rank matrices as well. We don't want to do it only for this. But suppose the rank is K, and suppose I pick 100 K rows, some large constant times K rows. Intuitively, without proof, we'll prove things properly later. Intuitively, that should pin down the row space of A, right? I mean, it's unlikely that I would miss something in the row space unless it's an anomaly. Okay? So if there's one row of A which is completely orthogonal to all the other rows, I'm sunk. My sample will not get that, right? So, and I'll miss some of the row space. But as long as that's not the case, as long as no small number of rows completely orthogonal to the other ones, I'll get the row space of A, essentially. This is intuitive. It's not assertions, right? So at least we can get the row space. Maybe we don't get an approximation to all of A, but we get a good idea of the row space. Okay. Now, suppose I pick order K columns of A. That should also tell me for the unsampled rows what linear combinations we need to take, provided things are not degenerate. So what do I mean? So I have a large matrix. I picked lots of rows, full rows. Okay. I pin down the row space of A. Now I pick a fair number of columns. They're not adjacent columns. Now, if I look at each, so let's say that I have an unsampled row here, and I want to figure out what combination of these sampled rows makes this row, right? So I know the row space. There's slice in the row space. Row space I knew from the sample. And I want to figure out what linear combination of the picked rows gives me this. Okay. How do I figure that out? I figure out what happens in the columns I sampled, only in those. I figure out what linear combination of these circled sampled entries gives me these, right? If I picked 100K columns, it should pin down intuitively. Everybody sort of see? I mean, so you know, I have, so to figure out what combination this is of the sampled rows, I have K unknowns, right? It's in K-dimensional space. So I have K unknowns to figure out. If I have 10K circles here, I have 10K equations. So if the system is reasonable, the 10K equations should tell me what the combination is. So I figured out a good idea of all the columns, all the rows, right, including the unsampled ones. So then I'm done. I'm not stuck with that problem, provided I have rows and columns. This is the intuition. So let's say that the matrix is not degenerate. Let's say the following thing, strong assumption. Every k by k subdeterminant is non-singular, non-zero. That's the usual definition of strict non-degeneracy. So then you're done, right? Now, less strict, this is a assumption that's made sometimes for data, is the rank is k of the whole matrix, but every 10k by 10k submatrix has full rank. Okay? Full rank is k. Not, it will be singular, but it has full rank. That's not unreasonable. But it's only an intuition, so. Okay, so the gist of the story is that if I pick a random sample of rows and a random sample of columns, I should be home. I should be able to approximate every entry of the matrix. We'll prove that, but we'll prove it, interestingly, using the matrix multiplication theorem twice, at least twice, right? We'll rigorously prove the error bound without assuming that A is low rank. This not an assumption we make, right? Okay, so the picture of what we are going to do. So we have a matrix A, which is big and fat in both dimensions. I'm going to pick some columns of A, which form a matrix C, right? I picked a few columns. This is as tall as that, yes, but not as broad. I picked some rows, that's a row sample. So this is as broad as A, but not as tall, right? And the assertion is I can compute from C and R, just given C and R, I can compute a U to put in between there so that A is approximately equal to C times U times R. You have to just convince yourself the dimensions are right. If this is S columns, it has S rows, let's say for the moment. This is an S by S matrix. Okay? The dimensions are correct and I multiply. Just a sanity check. Okay? So I'll state the theorem at the end, but the theorem is for every matrix A, if I pick a random sample of rows, columns and rows, according to length squared, that's important, then I can compute a U to put in between there, just from the sample, so that this is true. Okay. I'll spell out the error bound everything after a little motivation. So I think I'll give you one motivation. See, this is used in a bunch of contexts, but I'll give you one motivation. Suppose you have a large corpus of documents. Each document, as we did in the first lecture, is a word frequency vector, right? You just list how many times each word occurs in the document, right? So that's your vector. It forms a column of a large matrix consisting of many documents. Each column is a document matrix A, as we did in the first lecture. A new document, which is also a vector, comes in. We want its similarity to each document in the corpus. Or maybe we want a similarity only to the ones with which it's fairly similar. A very standard notion in information retrieval of similarity is dot product. You could use other notions, but dot product is a very standard notion. So we want the dot product of V with every column of A. That's the same as computing this, right? V transpose A. Okay. One of my aims in going through this is we'll revise a bunch of linear algebra as we go along, this part for sure. Okay. So here's a problem I want to solve. I want to pre-process A. I'm allowed a bunch of time. So that now query time means new documents being presented to me. And I must find the similarities vector quite fast. I don't want to spend n cubed time for that, right? But also, we better be accurate about this vector, but for every document V. So when I pre-process, I don't know which documents I will be faced with later, right? So I have to pre-process so that I'm correct, approximately, on every vector V. So we want to find a U, let's say, so that U is an estimate of V transpose A. So the estimate must not differ by more than delta times length of V. The length of V is because I can always scale V by a huge factor and the error will blow up, you can see. And this makes sure that it's scale invariant, right? So I don't want to blow up the error by scaling V. So I want this to hold, but for every V, no exceptions, because I don't know what the future holds, right? So this has got a name, right? So we'll set So we'll do this by doing the following. We'll just approximate, we'll find U to be just V transpose CUR. Okay, where CUR was in the last slide. But that is a fast computation. So that's a fast computation because I want to multiply by V transpose on this side, but C is tall and skinny, so the multiplication is not going to take so much time. Just think of the number of columns as constant. So it's just a constant number of dot products, right, instead of n dot products. And then multiply by U and multiply by R. So everything takes a constant number of dot products only, instead of n dot products. That's the saving we got. What about the error? I want the error maximized over all V, and I have to scale by the length of V to be at most delta. Okay. This quantity has a name. The left-hand side has a name. It's a spectral norm of A minus CUR. So this is a chance for me to say, please read up spectral norm if you've forgotten what it is. It is this. But anyway, it's the maximum over all unit length vectors of V transpose CUR, let's say. But the same as saying dividing by the length. Okay. If this was matrices were symmetric, it would be the maximum absolute value eigenvalue. They are not necessarily symmetric, so it's a maximum singular value. It's a maximum singular value of A minus CUR. You may not have seen what singular values are, you will soon, but eigenvalues certainly you know. So I want that to be small, but it's a randomized algorithm, so the random process can give you terrible results with very low probability, always possible. I just want the expected value of, this is called, the sub 2 denotes spectral norm. Okay. So I want the spectral norm squared to be bounded by something. We will prove that if I took a sample of S columns, it's bounded by 1 over S to the 1/3. 1/3 is not the best we know. We know better things now, but what we'll prove is S to the 1/3. So it's worse than the matrix multiplication where it was square root of S, now it's a cube root, where S is the number of sample columns. Okay. So it turns out I'm going to sample different number of rows than columns, curiously. So I'll put this down. So everybody understand, again I'll state the theorem precisely later, but everybody see what I'm saying. What I'm saying is any A, I pick a random subset of columns and a random subset of rows, S columns here, smaller number of rows, and then I can guarantee that the spectral norm difference is at most this much. The slight problem with proving spectral norm bounds, and that happens in a lot of other contexts when for instance, you have random matrix theory, spectral norm bounds require you to prove that for every vector V this is small, okay? So that's somehow not that trivial, right? You have to prove it for every one of infinitely many possible vectors. So Frobenius norm is a bit easier because it's the sum of squares. It's a fixed quantity. It's not a fixed quantity, right? It's many quantities. You must prove each one is small. Okay. So any questions on the setup? I should have said this on the slide maybe, but here's one question that could arise. So I proved in expectation at least, this is smaller than some epsilon times Frobenius norm of A, right? Okay, several questions can arise. First, can I put a 2 instead of F here? Second, can I put F instead of 2 here? Both would make things stronger, right? So let's consider the F and F. Can I do A minus CUR F less than or equal to epsilon times? The answer is no, but that's not possible. That brings me back to this whole thing, right? So that's not possible if A is essentially high rank, and simple example of that is the identity. So suppose A is the identity matrix, right? I pick a sample of columns of A, which is just unit vectors, right? a little bit of thought shows you that I cannot get such a fantastic approximation of A just with those columns, right? So I'm only giving you some unit vectors as columns. The rest of the matrix could be 0, or the rest of the matrix could be identity. Okay? Those two cases are completely different, and I can't distinguish those two from this. Okay? So there is no good low rank approximation to A. Oh, I should mention, this is low rank, obviously, right? This rank of this is at most S. There are only S columns, right? So, so another way to say this, maybe I should have said it clearer. There's no matrix of small rank that will approximate the identity very well in this sense, or any sense. I mean, so identity is essentially high rank. You cannot beat it. Okay? So any high rank, essentially high rank matrix that's where all the dimensions are high, you're in trouble. You cannot approximate. There's no free lunch, right? And actually, a similar thing applies to the 2 also. If I put 2's both places, that's also not valid. Again, for the identity. For the identity, that's just 1. The spectral norm of the identity is 1, right? So you cannot do that. Okay. So these are the best 2 things we can do on the 2 sides. Okay. So this time I came prepared with a lot of slides, so I won't run out of them. And the hope is I run out of time before, because otherwise it's getting perhaps from the heavier side. So I'm going to, because the last 15 minutes I'll go over this, but then I might repeat this the next time. So so first the intuition about this. So the intuition is interesting because it's very curious what I'm going to do. I'm going to take A and multiply it with identity, right? Using my lemma for sampling. I'm going to multiply it as identity. Of course, I know that A is equal to A times identity. So pretend multiplying A with identity, but by sampling. Okay? Sampling S columns, okay, of A. So we proved the matrix multiplication theorem, which said the error is at most going down as 1 over root S, right? And these were the Frobenius norms. Unfortunately, the Frobenius norm of I, the sum of squares of all the entries is n. So the Frobenius norm is the square root of that, right, is root n. This is not interesting, right? So this is useless, because to get anything better than Frobenius norm of A, I need S greater than or equal to n. So it's useless. So by the way, why is it useless to get Frobenius norm of A on that side? So suppose I want to approximate A, but I allow you error of Frobenius norm. So what can you do? This is trivial, right? It's not so interesting. But how would I accomplish this? How would I get an approximation like this? 0, right? So I could just take U to be 0, the 0 matrix, then this is true. Okay. So it's no good. So this pretend multiplication didn't help us very much, because I seem to need S at least n. But it will help us, you'll see. Now, for seeing how it helps us, let's pretend that R transpose is invertible. R is a sample of rows of A. Okay. R transpose is a small matrix. R looks like this. Again, I'll go over all this in a little slower next time. R transpose. This is R by R. This is likely to be invertible. Let's assume it's invertible for the moment. The proof works even if it is not. Why is it likely to be invertible? I pick a very small matrix, and if you're not degenerate, it should be invertible. If that's not obvious to you, don't worry, that doesn't matter. This is just an intuition. So R transpose, assume it's invertible. Then I can define a matrix P which looks like this. R transpose inverse we said exists, and I multiply by R transpose here in R, and it's not difficult to see that that acts like an identity on a particular space, on the space of R. Why am I saying this? I'm going to replace the pretend multiplication identity by P, and that will buy me something. That will get rid of the root n. Okay, and okay, maybe I wrote down a proof of this. Okay, so it acts as the identity on the row space of A, because if I have somebody belonging to the row space of A, I can write it as a combination of the rows. That's what I'm doing to X. So now P times X. So P operating on X is P is this, and X is R transpose Y. Now you get R transpose inverse, R transpose, they cancel each other out. You get R transpose Y, which is the same as X, right? So Px is X. So that, it means it acts like that, acts as if it was the identity on that space, right? Identity is what we want. And it's not difficult to see that perpendicular to that space acts as a null. The whole V-perp, perpendicular subspace, is revised perpendicular space is in the null space of P, revised null space. I mean, yeah, all of this should be known. So instead of pretend AI, I'm going to do pretend AP. Okay. Now P is somehow an identity on a very small dimensional space, R-dimensional space, whereas I was identity on the n-dimensional space. So the root n will get replaced by root R because it's identity on a very small space, right? And that's it. That buys us everything we want. We'll get a root R by root S here, where R can be made, it's under our control, we'll make it smaller than S. Okay? So we'll have to prove two things. We'll have to prove that, so there A was equal to A times identity, no problem. Here it's not true that A is equal to A times P, but it is in a particular subspace, but it's not in the whole of space. So we have to prove that the norm is small, the spectral norm is small. It'll follow from 1 and 2. We also have to prove next that we're going to prove that AP is close to CUR. So I want to prove A is close to CUR. I prove A is close to AP, and then I prove AP is close to CUR. And I do that by doing the following. I now want to do a pretend multiplication of A and P. I say C is a length squared sample of columns of A. I know how to do pretend multiplication, so I can do length squared sample of columns. I want to pick the corresponding rows of P. I will observe that, in fact, I can do that. That will look like U times R. Here's a hint why it might look like that, because P ends in R, right? P is something times R. So some of the rows of P look like U times R. We'll see that. So this is small by another application of the matrix multiplication theorem. So it is as if we are doing a multiplication of A and P by picking sample columns of A and sample rows of P. We don't do these multiplications. They are not actually algorithmically being done. This is for the proof, right? Okay, then I think maybe I shouldn't start the proof because we want to come back, revise all this, and then this was not the original proof. So this was later thought out by these tricks of employing matrix multiplication as a sort of conceptual thing for the proof. This is the conclusion. So the difference is bounded by some function of R as well as S. So unfortunately, R and S are not symmetric. Okay. So again, we have M by N matrix, R and S are any integers satisfying some conditions. Then actually, they don't have to satisfy any conditions. This is true for any R and S. So we have length squared columns, length squared sampling columns, length squared sampling rows. Then we can find a matrix U. Use S by R now, not S by S, to put in the middle so that this is true for spectral norm. There is a result for Frobenius norm, which I won't state, but